Hello, welcome to another Muffin Express Games graphics tutorial. I'm Joe Arroyo, and today we're going to be discussing the naive line algorithm. I'm going to go over where it comes from, how it's implemented in code, and then I will also explain why it's called the naive line algorithm and not the super awesome fancy line algorithm. So let's jump over to the whiteboard right away and get started. If you've been watching the tutorials, you may know this will be a quick recap. If you were to look at the pixels here on a screen, as I mentioned before, we have a finite array of pixels that we can set, right? And yet a line in math is an infinitely defined mathematical object. So how do we represent this with a finite number of pixels? And as I was mentioning, the challenge is that if we were to maybe set every pixel that the line touched, we'd find that that wouldn't actually be very efficient, and it would actually look kind of weird. So other than efficiency alone, there are areas where it looks too thick, and then areas where it's thin, and that just won't look right. It'll look a little odd to the eye. So what we're going to do instead is come up with 4 cases that explain the different kinds of lines we may come across and how we're going to approach them differently depending on what type of line they are, right? So case 1 is if the line is vertical. Case 2 is if it's horizontal. Case 3 is if the slope is very steep. And case 4 is if the slope is shallow. All right. Now the new question is, where do these come from? Why do we care if it's steep or shallow? All right. And to do that, I'll show you an example of, let's say we start with a steep example. Now what we would shade when it's steep, if we find out that the line is steep, we're going to take every row and only set 1 pixel per row. What we're saying is for every y value, we will only set 1 corresponding x value. If we did that, we would get something like this. And this looks a lot nicer, right? It's more uniform. All right. So corresponding to that, if we had a shallow line, we would do this. For every column, we would only set 1 pixel, which means for every x value, we will only set 1 corresponding y value. And if we did that, the line would end up looking like this, which again is a lot nicer. Now the reason why we make this distinction is best shown by giving you an example of what would happen if we had a steep line like this and we applied our shallow line idea to it. Now remember, if it was shallow, we said for each x value, we only set 1 corresponding y. Let's say we did that on a steep line. This is what would happen. So I can only set 1 y value at this x position. So there's 1. And then this one, I mean, it's like, what do I do? Maybe this one. And that's it. So that's all I get to set. And that's clearly a problem. So this is why we make the distinction between a steep line and a shallow line. And essentially it determines which axis we loop across and set only 1 pixel per each iteration. Okay, and then the only reason why the vertical and the horizontal are here is because in a way they're special cases where we can save a lot of computation knowing that we don't have to recalculate the x value in this case, and we don't have to recalculate the y value in the horizontal case over here. So it just makes it a little simpler, although we could technically apply just step 3 and 4 and it would draw all lines, but we don't need to do that. So let's go into the code and show how we can at least set up the cases that we have. So let's say we're making a function. We'll call it draw a line. And it takes, I'm going to make it take integers just because it's simpler in this case for explanation purposes. You could easily take floating point values. You would just have to round them. back to integers as soon as you got them, and that's the big difference. But other than that, it's pretty much the same concept. I'm just not going to bother with that so that I can type this out quickly. So let's just set up the cases. Well, the first thing we need to determine if it ends up being any of these cases is whether or not it's a vertical or horizontal line. We're going to do that by finding out the change in y, the delta y and the delta x. Okay, so let's do that. Our delta x is just the difference between the 2 points that they gave us, right? And our delta y is the difference between the 2 y values. Now I should mention the draw line function is just taking 2 points essentially, right? We're taking 2 x's and 2 y's, right? I could do x1, y1, x2, y2. That might make more sense. Doesn't matter how you pass them, but the idea is I have 2 points, right, being coupled together. So looking at this, now that we know our change in y and our change in x, right, we know that any vertical line, right, is going to have a change in x, a delta x of 0, because the x value doesn't change, right? So that's how we set that up, right? If our dx is 0, right, then we have a vertical line. Okay. Otherwise, right, if our delta y is 0, then we have a horizontal line. And those are our case 1 and case 2. That's simple, right? Otherwise, now we have more work to do because there's some kind of, we have to determine if the slope is steep or shallow at this point. So what does that mean we need? Well, we need that slope, right? So let's get the slope. The slope is the change in y over the change in x, right? That's what a slope is defined to be in mathematical terms, so we're going with that. Now, notice I don't care over here. I don't care if the slope is positive, right, or if it's negative. I just care if it's steep or shallow, because even if it's negative, I'm still only going to be setting one x value per y value that I iterate over. It doesn't change depending on whether it's positive or negative, which means we don't need to check that we need to check against the absolute value of the slope, because we just need to determine how much of a slope it has, not whether or not it's negative or positive. Now, how do we determine if it's steep or shallow? What really defines that? Well, that one's pretty simple. Just look at our axes real quick. And we know that a line with a slope of 1 will look roughly like that. It just means that if we move up 1 on the x, we reach the same point on the y. Pretend that's the same point, and the same thing here. Right, if we move by equal amounts on the x and the y axis going up, then we have a slope of 1, which means anything less than this, anything in this range, right, would be shallow, and anything in this range, right, would be steep. And this is how we would determine it, right? So if this is the margin that determines the difference here, the cutoff point, then we're just checking against to see if the slope is 1. So that's what we're going to do. So if the absolute value of the slope, right, is, let's do steep first. So if the absolute value of the slope is greater than 1, then we have our steep case. Otherwise, we have our shallow slope. Okay, so now we've set up all of our test cases. Now we just need to know how we're actually going to set the pixels in each one of these cases. So let's take a look at our vertical case first. So vertical, here's our vertical line. Just like that. Now remember, when we're drawing, when we actually get to the point in our pipeline where we're setting explicit pixels, we are in screen or viewport space, right? So if you saw from the other tutorial, our origin is up here, our positive x-axis goes to the right, and our positive y-axis goes down. And this makes sense. We're drawing, in scan lines, so we're going to do that, which would actually mean that the y max value is down here, right? And the y min value is up here. Okay. And what we're going to do is we're going to find the highest y value. So we're going to start at the highest y value, and we're just going to loop through all of the y's until we reach the min. And we should know that the number of pixels that we are going to set is just going to be the change in y, right? We get to reuse this delta y value, because if this was, say, 0, right? Let's say this equaled 0, which it does in our coordinate system in this example, and y max was, well, how many do we have? 5 here, 5. So y max would be 5. Then delta y is 5 minus 0, which is 5, which is also equal to the number of pixels we're going to set, which is right, 1, 2, 3, 4, 5 pixels. All right. However, the one thing that's important to note here is that we don't know that the first y or the second y is the one that the user's passing is bigger or smaller than the other one. We don't know what order essentially they're going to pass it to us in. So we have to determine the maximum, because if they gave it to us backwards, we could get this. Delta y would equal to -5, and we are not setting -5 pixels, we are setting 5 pixels. Okay, so we need to just account for that. But other than that, once we're done, we're just going to loop from the max. We're going to do it delta y times, and we're just going to keep the x value the same all the way down, and we're just going to set 1 pixel per y value, right? So let's do that. So the first thing we're going to do is take dy and set it to the absolute value dy. So now we know that dy is at least going to be positive, right? So that's what we're going to do. Then we're going to say while our dy is greater than 0, so that means we're looping dy times, because I'm going to decrement dy each loop. So for each iteration, then we're just going to set pixel where the x value stays the same and the x1 and x2 value are also the same. That's why it is a vertical line. So I can pick either x1 here or x2, doesn't matter, right? And then the one thing we need to do right before we go into this loop is we need to create a y value, and it needs to be equal to, as I just mentioned, right, the maximum between the two y values that were given to us, right? Now we know for sure that we're starting at the maximum y, and we're going to loop until we reach the minimum y, because we're looping dy times. So we do this. We set the same x pixel all the way down, but the y pixel we decrement each time, so that we're setting 1 for each row, essentially. Okay, simple. Horizontal has the same concept, so I won't over explain that. We'll just do the following. Change in x is equal to the absolute value of dx. Int x, right, is now equal to the maximum between our two x's. We're going to loop while our dx is greater than 0, so we are looping dx times, and we're going to set the pixel where our x value decrements each time, and our y value can be either y1 or y2. So now we have our vertical line and our horizontal line. Now, dealing with steep and shallow. Let's handle that now. Okay, so for a steep line, we're going to start there. We're going to need certain things, right? Let's grab a color. Now, for all intents and purposes, we can treat the y portion of the steep line exactly like we treat a vertical line. We know that we're going to loop through the y's and set only one pixel for y for each y. The difference here is that our x pixel is now variable. It can change. It's not always going to be the same. So we have to determine what that is. And we're going to do that by just using the very simple, the actual mathematical representation of a line. So we know that the definition of a line, or the equation for a line, is y equals mx plus b. We're going to use that. So we need to plug in, we're going to take the y value that we have at each stage in this line, and we're just going to plug it into this equation and solve for x, and then we know which x pixel to set, and we're just going to keep doing that every iteration, setting each x value on the way from the maximum to the minimum y value. Okay, so the first thing we need is the y-intercept, and this one's fairly easy to find because we are given a y and given an x. Here they gave us an x1 and a y1 and x2 and a y2. So as long as we use the corresponding y and x, we can just solve for b because we also calculated the slope, right? So y, well, let's say becomes y1, right? And x becomes x1 because we have those values. And now let's just solve for b. So we know that b is equal to our y1, right, minus our slope multiplied by our x1. So here's our y-intercept. And once we have that, then all we have to do for our steep line is let's just solve for x in this equation. Okay? So let's subtract b from both sides. So we'd have y minus b here, right? Finally, our x will be equal to y minus b over m. So this is our x value. So to see this in code, we go over here, we need to get our y-intercept, and this we solved here on the right. So our y1, right, minus m times x1. This is our y-intercept, and this is our slope. Cool, because we need the y-intercept for both the shallow and the steep, so I calculate it out here. But now that we're in the steep, we're going to loop through it as if it were vertical in this sense. Yeah, so we need to first take our dy, set it equal to the absolute value of dy, because we're going to loop dy times, just as before. Right? Our y value is going to be equal to the absolute value, sorry, not the absolute value, the maximum, forgive me there, between our y's. And then we're going to loop dy times okay, now we can't just set the pixel. Now we have to find an x every single iteration. And our x is going to be, equal to what we just solved for, right? Which is y minus b, but we have to take this whole term and divide it by the slope m. However, this would return a float, so we would have an issue here of truncation, so we need to round it, and I'm calling an imaginary round function right now. You'd have to write your own, but it's completely trivial. It's just if it's greater than or equal to 0.5, you round up to the top integer, and if it's less than that, you round down. And so we're going to round this off so that we get an integer representation of it, and then we can set the pixel. And we're setting our x and our y, and we decrement the y each frame, not frame, but iteration, and as we go through it each iteration, we calculate a new x because we have a new y. Okay, now we'll see for the shallow, it's exactly the same thing. You're just regurgitating this the other direction. So we get the absolute value dx of an int x, and it equals the maximum between our x's. Then we're going to loop dx times. Then we need to calculate a y each frame. And so we could say, I keep saying frame, each iteration. We could say that that we don't know this yet, but I mean it's right here. You're looking at the y is the equation of the line. So we know an x and we can get a y back. So we're just going to utilize that right here. So y is equal to our slope times the x value plus our y-intercept. Okay, now we can set the pixel. X decrements each frame, iteration, and y is what we're calculating, and then we're setting it. So for each loop here, we're going to set a new x pixel and calculate a new corresponding y position for the pixel. And in a nutshell, that's basically it. So you're looking at the vertical line case, horizontal line, what happens when we have a steep slope, and what happens when we have a shallow slope. All right, so this is the naive line algorithm. This can draw any line between 2 points that you pass it, simply put. Now, why it's called a naive line algorithm? Simply because you're looking at a lot of divisions. There's multiplications here. This is just the slope. This only happens once, not that big of a deal. You're looking at in areas right here when we have a steep or shallow line, so basically any line that has a slope of any kind really needs to sit here and do this subtraction and division and this multiplication and addition every single iteration of this loop. Right? And that can get expensive if you're drawing a lot of lines and you're drawing longer lines and that kind of a thing. So this is why it's called the naive version. It's because there are other algorithms such as the midpoint line algorithm where you can do this same kind of a concept entirely using integers. So it really saves all of these float calculations and the rounding and the function calls and things like that. That reminds me, down here you would have to round this off as well. So don't take this code to be perfectly compiling code. This is meant to be a pseudocode example of what you would do. So I'm sure there are some mistakes in there, but if you get the concept, then you'll understand what I was typing out live. So that's basically it. I will probably go over the midpoint line algorithm next. We'll see. So stick around. Next time we'll get into, I'll probably do additional line algorithms as well as go into some transformations in the pipeline, the specifics behind the model to world, world to camera, and each one of those matrices and what they do. So hope to see you next time on the next video. Take care.